So we're talking about how can you predict the concentration of a compound over time as as the reaction progresses. So, and there's going to be some equations in doing that, but it's really powerful stuff. I mean, I'm sure the equations might be a little more complicated when the reactions are more complicated, but it's the same idea that what's the amount of time for half the amount to disappear, or after so much time, what will be left? It's very useful. And you can use it to solve problems too on what's going on in nature. So what we're talking about are reactions that are of this form right here. Okay, so it's pretty much something reacting with itself or just decomposing, but it's very insightful. So these reactions, they can be first order, second order, or zeroth order. What's this order coming from again? Do you remember? We heard this word before. It was in what law? Rate law, right? You have the order of these different reactants, and the orders were the little x, what do we call them, Monica? Little exponents, right? The little exponents in the rate law. So that little exponent is either a 1, a 2, or a 0, but we don't even need to figure that out because they're going to tell us. Hey, this is the first order reaction. Find the concentration. Okay. So here's some equations for us to use. We just need to know how to use these things. Wow, it doesn't erase. Okay. If I had bracket, what does that mean, the brackets? Daisy, what did those mean, those brackets? Starts with the C. Concentration. Good. What units do they like to use for concentration? Big M. And you can write, instead of writing big M, you can write what over what? Moles over liters, but big M's a lot easier, right? Call it molar or molarity. So if I have bracket A with a little t on it, like this variable right here, what would that mean, Jonathan? More than likely. The concentration of A at, not temperature though, it's little t, time, at some time. They're going to tell us a time, and you want to know what the concentration is. That's what this will be. What about this one, Anessa? They don't have a T on the bottom. They have a 0. And that's in here, too. Like, here it is. The initial concentration. Good. I don't know. For some reason, they're too lazy to write T equals 0, right? That's our initial. Okay. How about little t? Monica, what would you think little t would be? Yeah, it's just time. Probably what units? They're going to want seconds. They're going to want seconds. Okay. Oh, we have a K. Anybody recognize this? What was this called? Roland, what was that called? Yeah, that's from the last formula. It was called the what constant? The rate constant. Okay, that's the same thing, the K. There's one left. T with a little 1/2 on it. Anybody know what that's called? Kind of, pretty much halftime. Half-life. Half-life. The time for half of it to disappear, for half of A to react. Okay. So what it's going to come down to is they're going to tell us the order. We picked the equation because we know what variable they're looking for. They're after the time. Fine, right? We'll solve for it. But pretty much you're going to have to substitute all those numbers in, and one variable will be left. And that's going to look like one of these. For example, if it's this one, which equation are they really substituting into? Can you see it? The first one. I don't know, I can't erase anymore. Yeah, it's going to be that first one, right? Because you can see that K must be 89, right? They're solving for T. The concentration of A at time T was this number. The initial concentration was that number. So you read the question, you plugged all the numbers in, now you got to solve for T. So Anessa, what would you do first to solve for T on this thing? Ooh, good. Now, what is the ln? Natural log. It's on the calculator. So we'll do the ln part first. Get a number. Then do what? Then divide it by the negative 89. So when you look at these, have a picture of what to do on your calculator before you see the whole route, how to solve for T, before you start plugging stuff in. Otherwise, you might do something in the wrong order. So find what's on the ln side first. Right? Divide these two, hit equals, take the natural log, divide by negative 89. You should have your answer. Okay? 6.3 times 10 to the negative 3. Take the natural log. Where is it? There it is. My final answer is about 0.02. Did you get it? So divide 6.3 times 10 to the negative 3, divide it by this one, hit equals, take natural log, divide it by a negative 89. Did you get it, Jonathan? Okay, 0.02. After you divide these two, because it's ln of this stuff. Yeah. And again, they don't like to write parentheses. They could. It would look better if they did, but a lot of times they don't. Okay. How about B? Jasmine, how would you go about solving for B? Oh, good. Moving the variable from the bottom to the top. Except we're going to need to do that. But first, we got to get rid of this ln. Right? You see what she's talking about? We're going to have to do this. We're going to have to move this guy up to the top. But we can't do it yet. Ah, this dang thing. We got to get rid of that ln first. Anyone remember how? Oh, my gosh. How do you get rid of ln? Wow, what was that? How do you get rid of ln? Does anybody know? The e. So let's see what this looks like. Raise both sides to the e power. All right? These end up canceling on you. So you end up with just 2.49 times 10 to the negative 5 all over A0 equals e to the negative 35 times 5. Okay. Now we do what Jasmine was talking about, right? Switch these guys. Okay. It's going to be an extremely big number. Right? So A0 will come up here. This e will go to the bottom. See if this works. Now, do you see E on the calculator? It's orange. So you have to hit Shift first, right? So what I'm going to do is, all right, we'll bring it down there. Let's do it in a couple steps so that we can make sure everyone's getting the same numbers here. So 35 times 5. Do that part first. Hit the plus minus. So this is a negative 175. Now I'm going to push Shift e to the x. Now I get this huge, extremely small number. 9.96 times 10 to the negative 77. Okay? So that number has to go on the bottom. A0 goes up on top. So about 2.5 times 10 to the 71 or so. It's a ridiculously large number, but we're just playing with the math anyway. Jasmine, did you get it? Okay. This has to be, take 5 times 35, make it negative, push Shift e to the x. Do you see it on the calculator? E to the x? Yeah. It's orange though, you got to push Shift first.
I do the first 35.
So 5 times 35, hit equals, make it negative by putting plus minus, and then Shift e to the x. Okay. Let's try one more before we see if we can get C. So what's the game plan on this one? Victor, what would you do to get this one? Yeah, we're going to have to do that cross multiply thing you're talking about, but not yet though, right? Because get this whole number. Get that whole number. Then do the cross multiplying thing he's talking about. You bring it down to the bottom. Bring A to the top. Now, one thing that you should know about your calculator, not the big ones, but with these, they follow the order of operations. I don't know why yours don't. They follow the order of operations. What that means is if you take 2 plus 3 times 6, just literally type that in the calculator, it has to do multiplication and division first. It forces itself to. So it's going to hang on to that 2. It's going to figure out what 3 times 6 is first and add it to 2. So that means you can literally plug this all in the calculator without doing anything. Take 12 times 18 plus 1, divide by 2.4 to the 10 negative 4, and you'll have the answer. You just kind of got to trust it. I got about 4,382 or something. Okay, now that's in the calculator. Now another trick to using these that I use all the time is I have to bring that to the bottom, right? So it's going to be 1 over. There's a nice little 1 over x button here, so you don't have to type in anything. It is orange though, so push Shift 1 over x, and there's your answer. You just flipped it. 2.28 times 10 to the negative 4. Oh, I guess you should put units, big M. So you can do this later at the end of the hour if we have time. Okay? It's pretty much the same thing again. So let's try some problems. Now before we hit the problems, I want to go over this curveball. Because working these problems, man, you should definitely have your cheat sheet right next to you. All these equations, right? So you're reading these questions. they want to know what is the concentration of A after some time. So it looks like you have to find an equation and solve for this, right? Where T is going to be 5 seconds, 20. No. This is a conceptual question. It's a half-life question. So in that sense, it's kind of a curveball. And this, I'll show you the trick. If you have 5 seconds have gone by, how many half-lives is that? It's 1 half-life. So that means whatever you have, you multiply it by a half. Let's not do the answer yet. How about number 2? How many half-lives went by in number 2? Each half-life is 5 seconds. We have 4 of them. So that means 4 half-lives had to have gone by. 1. Oh, heck, let's just write to the 4th. I don't know what happened to my eraser. Let's just write to the 4th. But it's 1/2 written 4 times. Now all we do is multiply it by our original concentration. We'll have our answer. So the original was 2 molar. So in part 1, multiply this times 2 molar. Multiply this one times 2 molar. In part 3, I think it's 6 half-lives, isn't it? So you'd have 1/2 to the 6th times the original concentration. And those are your answers. And to get 1/2 to the 6th, 1/2 is 0.5, so 0.5, and there's your x to the y button. And just push it and type in 6. And you get 0.0156, take it times 2, 0.03125. So this answer is 0.03125. All right, the first one, I guess, would just be 1 molar. And you got to take a half, 0.5 to the 4th times 2, well, 0.125 molar. All right, does that make sense? So on these half-life questions, you got to be careful, because I always want to go digging up an equation for them, but they're not. It's a conceptual thing. Okay, so just watch out for that curveball. Are we good so far? Monica, does this make sense? Okay, so before we go and start working these questions that look like this, right, giving us all this information, we got to pick an equation. There's one more conceptual thing they want us to talk about, and that's how to sketch potential energy diagrams for exothermic and endothermic reactions. Well, I want to show you this little skateboard dude first. Okay, here's a skateboard dude. So this is the potential energy surface. He wants to go from here. Why is he swinging so much? Slow down. He wants to go from here to over to here. Would this be an endothermic or exothermic process? Exo gives off heat. Exo gives off energy. Endo absorbs energy. So which one is this? Pretty much all you can do is compare where he starts and where he ends up. Doesn't matter how he got there. Does he end up at a higher energy? He does. So this has to be endo, right? Because he's ending up at a higher energy. So you get the little guy, and you apply a bunch of energy there, and to stay. Okay, now he's there. That was an endothermic process. Now the exact opposite. I want him to go the other direction now. Exo or endo? Look at the beat. Now he's starting here. He's ending up here. So is he ending up at a lower energy or a higher energy? He's ending up at a lower energy. So that energy has to go somewhere. It's giving off his heat or whatever. So in this case, it's giving off his speed. But this would be exo when he's going that way, right? So you get the guy, give him a little energy, get him to go. Come on, get over the hump. There he goes, right? Okay. He's gone. So what we need to do is know how to, like on endo then, you have to start really low, end up really high. That's the whole idea of endo. And then there needs to be a hump in between, an energy hump. So just sketching a little energy hump. And if you want to draw these curvy on the bottom or flat, it really doesn't matter. Okay. So our reactants and our products. And we need to label the axis. So this is potential energy. And the book wants you to call the x-axis reaction coordinate. Now, I don't like that word, but it's not very visual. Reaction progress is better, or time maybe even, but that's fine. We need to also label energy of activation. That's just the energy that the reactants need to get converted to products. That's the energy of activation, EA. And then our enthalpy. That's always the energy difference between reactants and products. Okay, that's pretty much all we need to know how to label. But we have to do it also for exothermic. What changes? Yeah, go from high to low. Go from high to low. Reactants start high, end up with products really low energy. Draw your hump. Label now your energy of activation. Look how tiny it is. This little hump is all you need. Exothermic reactions are much more spontaneous, right? And then the energy difference between reactants and products is your delta H. And don't forget to label your axis. My English is so bad. Okay. All right, that makes sense? Got it all? Endothermic and exothermic potential energy diagrams. Okay, so have your cheat sheet out. Let's try this first one. A reaction of the form. Okay. Let's pick on Jonathan. What variable in this cheat sheet with all these equations, which variable are they after in this question? Yeah, for this first one, is 59. Which variable are they after? After what? Read the question. See what it's saying? It wants, what is the molar concentration of A after 35.4 seconds? It's the bracket A, but which one? You have two of them to pick on. All right, you have this one, or you have this one. Now, he says it's the one with the T on it. Do you agree? Yeah, because this is the initial. They gave you an initial, right? So we're after A at time T. Now, Roland, we need an equation. Which one would it be? Now, but doesn't it say? It says second order, though. So you've got two of them to pick from on second order. First one, because the other one doesn't have the A in it, in the A at time T. So we're going to do the second order. Just copy it down here. Okay. We solve for this. They gave us everything else. Substitute it all in. Make sure the units are compatible. I'm pretty sure they are. Seconds and moles over liters. We're all good there. You don't have to do any converting. Just substitute it all in and solve for the unknown. Should work. have your game plan, right? Get the entire right-hand side, get one number, then just flip it. You know, it should work. Monica, what'd you get? 0.878. Anybody else get 0.878? Let's try it. 0.225 times 35.4 plus 1 divided by 0.293, and then flip it. Did you get 0.0878? Yeah, 0.0878. Or 0.088 or something. You didn't get that, Jonathan? Okay. Roland, you got it? Okay, so then this has to go up where it is, and it goes on the bottom. So I just put shift 1 over x. And you have to push shift because 1 over x is orange. Okay. Comfortable with it? All right. Let's see if I can get you uncomfortable. Try this one. This is as hard as I can possibly make it, is this question right here. But we can do it. Okay, what's making this one so hard? Do you see it? It's the first one, but it's first order. Yeah, there's a bunch of molars in there. But let's just focus on the question. This part. What was the concentration after 750 seconds? Right? Let's just plug it in for that. You said it was first order, right? So if we wrote the first order equation, I was copying this down, equals negative KT. Okay? Well, the time is, so we're after this. We want to find this, right? Isn't that what it is? We want to find that, because what's the concentration? What's T? 750. What's the initial? 0.0015. What's K? Right? So how I'm approaching this is I'm starting out with, yeah, they can make it as complicated as they want. You still may not see how to do this, but what I'm saying is they can make it as complicated as they want. Start out with what they want. This is what they want. They want first order equation and solve for this guy. So you do everything you can. You find out, oh, I don't know what K is. That's probably what all that other stuff is for, right? So you have to find K first. So once you find it, then you can plug it in here. And how do you find K? With all this information. told you everything you need to know to find K with that first part. So step 1, find K. Step 2, plug in and get your final answer. So try it. Temperature, did that have to do anything to do with anything? Right? Temperature's not even in our equations. We don't even care. If they told you what Half-Life was, that'd be really easy, right? That'd be awesome, because all you'd have to do is move K up here and move Half-Life down there. Oh, that'd be awesome. But they didn't. Right. So plug in these two numbers first, see what that is, take the natural log of it, divide it by a negative 455, and you'll have your K. So I must find out what's inside the log, the natural log first. Once you find your K, then you can plug it in. Solve for your final answer.
So how is it that you do the LN one? Because I don't know that.
It's right there next to the on button.
Yeah, but do you press it first and then you write this?
No, no. You have to find out what it is first. Because when you push LN, it gives you that of that. Okay. So I'm going to raise both sides to the E to get rid of that natural log. Raise this to the E, then pretty much take it times 0.0015. And I'll have my answer. right? So if I raise both sides to the e, ln's gone, I'll just have e to this. But then I got to bring the 0.0015 up there too. Now, depending on your rounding, you might have a little bit different answer, but it should be pretty close, depending on how many digits you carry.
So you want to multiply these two and then
Don't forget the minus sign, though. You have to multiply those two, make it negative, and then raise it to the e. Then take it times 0.0015. We'll get it. Okay.
go to the e and then multiply by 0.007.
Yeah, because that will be this side. You'll have a number here. But then you got to get the 0.0015 up there with it. So take it times 0.0015. Times 10 to the negative 3? Yeah, it's fine. See, because when I'm doing this stuff in my calculator, I don't erase this number. So my number is really long. So some people might have just done 5.09. Well, they're going to get something different than you. So if you want to get the answer in the back of the book, you can never really write anything down. You have to go from pretty much here to here, and your answers will match the back of the book perfect. But if you write stuff down, right, like this, if you write this down and you don't carry all the digits in the calculator, you're not going to get the exact same answer in the back of the book. It'll be close, but not exact. Okay. That's good enough. Something like 10 to the negative 3. You're doing it right. Let's see. Where is the? I thought there was this percent problem. Oh, where is it? Oh, this. Let's take a quick look at 65, and then we'll let you go. Okay. So they're asking for how many hours would be required to decrease to the following values. If I would have said 50% left, the number of how many half-lives would that be? If I said 50%, 1. If I said 25%, 2. What's the next one? Keep dividing by 2. Half of 25 is 12 and a half. That's 3. Divide that by 2 again. It's 6 points. See how what they're doing here? They just keep dividing it by 2. It's 4. That's 5. So pretty much all you have to do is figure out what a half-life is. Okay? And that's what the question is. Find out what a half-life is. And then if it's 1 half-life, well, then that's your answer. If it's 2 half-lives, take it 2 times the number of half-lives. If the half-life is an hour, the answer would be 2 hours. Take it times 3, times 4. Right. So let's find out what the half-life is. But this was the confusing part, these percents. They say the rate constant is this, and it's first order. Isn't that the one that you're talking about, Daisy? Yeah. The half-life is 0.693 all over k. So the half-life would be 0.693 all over, what did they say k was? 2 times 10 to the negative 6. But that's seconds, so we're going to have to do a little converting. 346,500. That's seconds. They want the half-life in hours. So how do you convert this to hours? How many seconds in an hour? Well, yeah, it's 3,600. But 60 seconds in a minute, 60 minutes in an hour. Pretty much you're dividing by 60 twice, which is 3,600. So about 96 hours. So that's our half-life. That's part of our answer. Then they wanted to know, so my answer for one half-life would just be that, 96.25 hours, right? Two half-lives take 96 times 2. Three half-lives take 96 times 3 and 4, right? And that's the answer for all those. Okay. So work on them. I'll be glad to help you out. Just give it a shot first and then come by.